At this point, we have explored kinematics and forces in rotation. In this video, we will investigate work and energy in rotation. We previously defined work as the practical effect of a force, how it actually changes the position of an object. In this image, the coconut is not moving, so the forces acting on it are not doing work. In this video, the coconut is falling. The weight force is doing work. Just like displacement, velocity, acceleration, mass, and force, there is an exact parallel for work in rotation. If linear work is the practical effect of a force, how a force causes displacement, then rotational work is the practical effect of a torque, how a torque causes angular displacement, how a torque causes spin. Both forms of work are scalars, measured in joules. They are symbolized with the letter W with no vector sign. In its linear form, the calculation for work is familiar. Work equals the size of the force multiplied by the size of the displacement multiplied by the cosine of the angle between them. In rotational form, the calculation is analogous. The rotational version of force is torque, and the rotational version of displacement is angular displacement. That gives us work equals size of torque times size of angular displacement times the cosine of the angle between them. For our purposes, we will only examine two possible values for that angle. Suppose the torque and the angular displacement are both clockwise. Then their vectors both point in k hat. The angle between the vectors is 0, which makes the cosine 1, which in turn makes the work positive. Similarly, if the torque and the angular displacement are both clockwise, then their vectors both point in negative k hat. Again, the angle between the vectors is 0 and the work positive. So if the vectors point in the same direction, both clockwise or both counterclockwise, the work is positive. On the other hand, if the torque is counterclockwise but angular displacement is clockwise, or vice versa, then one vector points in k hat and the other in negative k hat. The angle between them is 180, which makes the cosine negative 1, which in turn makes the work negative. This is the same pattern as in linear work. When a force pushes an object in the same direction as the displacement, it does positive work. When it points in the opposite direction, it does negative work. Remember, in linear work, if an object doesn't move, there is no work. Likewise, in rotation, if an object doesn't spin, there is no work. So for instance, in a statics puzzle where there is no motion, the forces do 0 work and the torques do 0 work. Let's see a simple example of rotational work, a gyroscope. The string applies a tension to the side of the shaft, causing it to rotate. It accelerates as the full length of the string is pulled out. Consider this puzzle. A gyroscope with a shaft radius of 0.01 meters is initially at rest. It is wound with a 1 meter string. The string is pulled with a tension of 5 newtons. How much work does the tension do to accelerate the gyroscope? We'll start, as always, by drawing a picture of the system. So this is what a gyroscope looks like from above. Here's the disk, and this small circle is the shaft. Now, initially, the rope is wrapped around the shaft, something like this. But by the end, the rope has gone away and the shaft is rotating by itself freely. So this here is photo 1, and this is photo 2. Now, let's put in the axes. I'm going to put my axes in the conventional way. And now let's put in the information that we know. We know that the string had a length of 1 meter. The tension in the string was 5 newtons. You can write it like this. And we also know that the radius of this shaft is equal to 0.01 meters. So that's 3 pieces of information that we were told. And we're going to use all this information to find out the work that was done. Let's go ahead and get started with that. Work depends on torque and on displacement. So, or more correctly, torque and angular displacement. So let's first find out the angular displacement of this shaft as the string gets pulled out from it. So if the string is being pulled out without slipping, then this relationship is going to hold. The linear distance traveled by the shaft is going to be equal to the angular displacement multiplied by the radius. So let's put in everything that we know. We know that the string had a length of 1 meter. If it didn't slip on the shaft, then that means that the shaft must have rotated by 1 meter as well. Is equal to the angular displacement, as yet unknown, multiplied by the radius, which is 0.01. So, simplifying all of this, we get that the angular displacement must have been equal to 1 divided by 0.01, which is 100 radians. And since when you pull on this, this is going to cause the gyroscope to rotate this way, that is counterclockwise, as we see in this picture, that means that that is going to be the positive direction, so we can put a K hat over here to symbolize that. And yeah, so now we have found out what is the angular displacement of the shaft as the tension is acting on it. So that's the first piece of information. Now the second piece of information is, what is the torque that this tension is exerting? We know that the size of torque is given by the lever arm times the size of the force times the sine of the angle between them. So that's going to work out to, the lever arm is, in this case, just the distance from the center of rotation to where the force is being applied. That's equal to the radius of the shaft, which is 0.01, times the force, 5 newtons, times the sine of the angle between them. The lever arm in this case is oriented horizontally. So if I were to draw a vector that points from the origin all the way to where the force is being applied, where the string ends, over here where it starts contacting with the shaft, that vector would point horizontally. But the string itself is pointed vertically. So that is a 90-degree angle. This would be the sine of 90 degrees. So if we were to solve for the torque being caused by the tension, that'll work out to sine of 90 is 1, so we get 0.01 times 5 times 1, which gives us 0.05, and the units of torque are newtons times meters. Last step is, what is the direction of the torque?
Well, we can say that this is a torque which is going to tend to rotate this shaft counterclockwise. That's positive. So we should say 0.05 k hat newtons per meter. We could, if you wanted to do it the way that we did it in our 103 class, we could say the lever arm is pointed rightwards, the force itself is pointed in positive y, so that means the torque must be pointed out of the page, but that's basically a positive torque, which means once again we're talking about a positive k hat over here. So now let's sum up the things that we have found. We have found the displacement, that is important, and we have found out the torque, that is also important. Now, we just need to put all this information together to find out what the work is. Work is defined as the size of the torque multiplied by the size of the angular displacement multiplied by the cosine of the angle between these two vectors. So the size of the torque was 0.05 and it was pointed in k hat. That's the torque. The displacement was 100 k hat. And the angle between them, let's see, both of these are in k hat. Both the displacement is in k hat and the torque is in k hat. That means that these two vectors are really pointing in the same direction. So that would be the cosine of 0. So all of that's going to work out to 0.05 times 100 is equal to 5 joules. That is the amount of work which has been done by the string as it causes an angular acceleration on the gyroscope. So we had to solve for the rotational displacement, the angular displacement. We solved for the torque, and then we used the formula for work to find out how much work was done. It was 5 joules.
So the string did work on the gyroscope as it was pulled. And we now see the gyroscope moving, or more specifically, rotating. That means it has kinetic energy. Just as there is a rotational analog of work, there is also a rotational analog of kinetic energy. Linear kinetic energy equals 1/2 mass times velocity squared. The rotational form of kinetic energy is exactly parallel. It is symbolized as Ke sub ROT. The rotational version of mass is moment of inertia. The rotational version of velocity is angular velocity, the spin rate. So the kinetic energy of rotation equals 1/2 the moment of inertia times the angular velocity squared. Now for the most important part of this video. Earlier, we wove work and energy together into the law of conservation of energy. This is one of the cornerstones of physics. The law of conservation of energy says that the energy of an object must stay constant unless it gains energy through work in or loses energy through work out. It turns out rotational work and rotational kinetic energy slide into this equation effortlessly. You can plug them into this equation just as easily as any of the linear terms. The law of conservation of energy is powerful enough to give them a home too. And we're going to explore this in several examples. Let's start by expanding the gyroscope example. Since we know how much work was done by pulling on the string, let's relate that to the kinetic energy of the gyroscope. Let's revisit the earlier puzzle but add a part B. If its final angular velocity when the string was pulled is 60 radians per second, what is the gyroscope's moment of inertia?
In the second part of this question, we were being asked to find the moment of inertia of this gyroscope. Now, this gyroscope has an irregular shape, so trying to find it out by direct integration or some technique like that is not going to be all that easy to do. All that said, however, let's see if we can find it out using energy. Let us use our trusty equation, conservation of energy, one of the fundamental rules of the universe. Conservation of energy says the kinetic energy in photo 1 plus the potential energy in photo 1 plus the amount of work that comes in, the work gained from forces, minus the work lost through forces, is equal to the kinetic energy in photo 2 plus the potential energy in photo 2. Now, in photo 1, the gyroscope is not rotating, so there's no kinetic energy. We are not dealing with a change in height anywhere, and there are no springs in this question, so there's no potential energy. But there is most definitely work in. We found it, 5 joules down here. So work in is present. We're not dealing with friction, so we don't need to bother with work out. Kinetic energy. There is going to be rotational kinetic energy here, not linear kinetic energy because it's not translating, it's not moving linearly, but there is rotational kinetic energy as this is spinning. So kinetic energy too, we have to keep. But again, there's no change in height, there's no springs involved, so there's no potential energy in photo 2. So that means that conservation of energy is now going to simplify down to the work in is equal to KE2. So, how much is the work in? We just calculated it, 5 joules. And what is the definition of KE2? Kinetic energy is equal to 1/2, in rotation, it's equal to 1/2 I times omega squared. Omega being the spin rate, the angular velocity. So, now that we have all of this information, and especially since we were told that the spin rate is 60 radians per second, we now have enough information to solve for what I is. So, it's just substitution. 5 is equal to 1/2 times I, that is the moment of inertia, the difficulty of changing the spin rate, multiplied by the spin rate itself, 60, squared. So 5 is equal to 1/2 of I. 60 squared is 3600. And half of that is going to be 1800. So all we have to do is divide both sides by 1800, and that'll give us the moment of inertia. So 5 divided by 1800 gives us 0.00277 repeating. So let's write that like this. The moment of inertia equals 0.00278, let's call it. And moment of inertia is always measured in kilograms meters squared. So now we have solved for the moment of inertia despite the fact that we didn't have enough information to perform a direct integration. We knew very little about the geometry of this object outside of the fact that its shaft had a radius of 0.01 meters. And despite that, we were able to figure out the moment of inertia because we found out how much work was done when a force was applied to it, and that work can be related to moment of inertia times velocity squared. So this here is the approach for solving for the moment of inertia using energy considerations. And this is the first time that we have used conservation of energy using rotational work, which slides right in, and rotational kinetic energy, which also slides like a glove.
We can use rotational values in concert with potential energy as well. Here, we see a rod swinging back and forth. This counts as rotational motion. This setup is called a physical pendulum. At its maximum height, the pendulum obviously has gravitational potential energy. But now we have a problem. Potential energy due to gravity equals mgh, mass times gravity times height. But as the rod swings, which point do we follow to figure out the height? The answer is we have to follow the center of mass. Remember that for a uniform regular object, the center of mass is in the physical center of the object. That's the point we need to track to calculate the height for gravitational potential energy. Consider this puzzle. A uniform 4 kilogram 1 meter rod is attached to a wall via a hinge at one end. It is initially oriented horizontally and then released. What is its angular velocity when it passes through the vertical position?
In this question, we have a rod that is circling around a hinge which has been attached to the wall, something like so. And in this, so this is going to be photo 1, that corresponds to where the rod was horizontal. Now where the rod is vertical, it's going to look something like this. This rod, of course, is attached here, and it's able to spin freely without friction. So now that we have the picture down, let's set some axes. So this is first of all photo 2. I'm going to set them in the conventional way. Rightwards is x, upwards is y, rightwards is x, upwards is y. Now let's start writing down some information about this rod. So it has a length of 1 meter. It has a mass of 4 kilograms. And we were told that it's going to swing through this angle over here. I also said that when you're keeping track of the height for when you have to do the potential energy calculation, you need to keep track of the location of the center of mass. In a uniform object like this rod, the center of mass is in the geometric center of the object. So that would be here when the mass is in this orientation, and over here when the rod is in this orientation. So if we want to know how far the rod has fallen, we have to do it on the basis of center of mass. Okay, so initially the center of mass was aligned with the x-axis, but then it falls to this position over here. And since this is the center of mass is exactly halfway down the rod, and the rod has a length of 1 meter, that means that the center of mass must have fallen by half of that. So this is 0.5 meters that the center of mass has fallen. That is pretty much a rundown of the basics that we need to know for this particular question. Probably the last thing that we need to figure out is the moment of inertia, and then we'll be able to run into conservation of energy. For a rod that's being rotated around one end, the moment of inertia, symbolized by the letter I, the difficulty of rotating it, is given by the mass times the length squared divided by 3. And we know this because this is an equation that happens to be in your textbook. This is the standard equation for a rod being rotated around one end. Mass is 4, length is 1 squared, all divided by 3. So 4 times 1 squared divided by 3, that's going to give me 4 kilogram meters squared. So this is a useful piece of information. It is going to become necessary later on down the line. All right, so now we have all of this information, this preliminary work that we've done. We are now ready to jump into conservation of energy. Conservation of energy says that the kinetic energy in photo 1 plus the potential energy in photo 1 plus the amount of work that came in due to any forces acting on this, like jetpacks and things like that, minus the work that went out due to friction, is equal to KE2, kinetic energy at photo 2, plus potential energy at photo 2. Now, let's start erasing the terms that we don't need. The rod is at rest in photo 1. There's no kinetic energy. But the center of mass is at an elevated height relative to where it ends, so there is potential energy. The work in, this doesn't have a jetpack strapped to it, so there's no work in. Work out, there's no friction, there's no work out. Kinetic energy 2, this physical pendulum is indeed going to be moving when it reaches this point over here, because if this is the extreme of motion, it's going to swing through and then overshoot the horizontal position. So the kinetic energy 2 is indeed there. And finally, potential energy 2. Well, it actually makes more sense to think of, because we said that this was the origin over here, I'm going to backtrack on something that I said. The potential energy 1, I am actually thinking of setting to 0. And the reason is because the center of mass is right now on the x-axis, which is our 0 height. It's where y equals 0. So, on the understanding that it's going to descend from there, the height in potential energy 2 becomes negative. So I'm going to set potential energy 1 as being 0. So what does this all work out to? It means that 0 is equal to KE2 plus PE2. Again, on the understanding that potential energy is now negative because this object has descended below the x-axis. Remember, potential energy due to gravity can absolutely be negative. Kinetic energy can't be. Let's expand these out. 0 is equal to KE2. This is a rotational kinetic energy, so that's 1/2 I omega squared, and this would be omega 2 squared, plus the potential energy is going to be given by mgh. Now, let's plug in everything that we know. 0 is equal to 1/2. The moment of inertia, I should have written 4/3. It's 4/3. Times omega 2 squared plus mass 4. Gravity 9.81. Height, in this photo it has descended below where it started, so that means that the height is actually going to be negative 0.5. Now, let us simplify all of this. 0 is equal to 1/2 of 4/3 gives us 2/3 of omega 2 squared plus 4 times negative 0.5 gives us negative 2, multiplied by 9.81 gives us negative 19.62. Moving this over to the other side, we get 19.62 is equal to 2/3 omega 2 squared. And now we're in the home stretch. 19.62 divided by 2/3 gives us 29.43. So omega 2 squared is equal to 29.43. Therefore, square root of that is 5.42. So the magnitude, the size of the spin rate, the angular velocity, is 5.42 radians per second. So in this case, what we did is we used our understanding of rotational kinetic energy and combined it with potential energy. Now, some things to be careful of here. We first had to work out what the moment of inertia is. Apologies, by the way, for that misprint earlier, but it really is 4/3. The potential energy, again, because we set the horizontal axis to be at the original position, this has fallen by 0.5 meters, so I had to set the final height as being -0.5. It's below the x-axis. That is allowed for gravitational potential energy. But really, the rest of it was just math, and we were able to solve for the rotational speed, the size of the rotational velocity, the size of the spin rate, directly using conservation of energy.
In this pulley system, we see an extra layer of complexity. The bucket moves in linear motion, but the wheel rotates. So that means there are two forms of kinetic energy: the regular linear kinetic energy of the bucket and the rotational kinetic energy of the wheel. We have to account for both in conservation of energy. Fortunately, if the rope doesn't slip on the pulley, the two are closely related. Consider this puzzle. A well has a pulley wheel with a radius of 0.1 meters and a mass of 2 kilograms. A 5 kilogram bucket is hoisted over the wheel. It starts from rest and then descends an unknown distance. Its velocity when it hits the water is 8 meters per second. What is the bucket's initial height?
In this question, we have a bucket which has been suspended over a well, something like this. And it is initially at rest. So at photo 1, it is at its highest point above the surface of the water. But as we get to photo 2, this rope starts moving and the bucket starts descending. The pulley wheel is reasonably massive, so some of the original energy due to the potential energy of the bucket is going to get transferred not only to the KE of the bucket, but also the rotational KE of the pulley wheel. So it might look something like this. Okay. Now, typically, we set the origin to be at the center of the pulley wheel, and this is not going to be any exception. I'm going to set my origin and my axes in the conventional way. That's Y, that's X, that's X, that's Y. Now, let's write down the information that we know. The mass of the bucket is 5. For the pulley wheel, the mass of the pulley wheel is 2 kilograms. The radius of the pulley wheel is 0.1 meters. And that's largely everything that we have been told. We want to find out what is the height through which this bucket descends. As you probably guessed, one of the things that we're going to have to do is to figure out the moment of inertia of this pulley wheel. So let's go ahead and do that. The moment of inertia is given by, for a disk like this, 1/2 mass of the disk times the radius of the disk squared. So that's going to work out to 1/2 mass 2 radius 0.1 squared. Half of 2 is 1, 0.1 squared will give us 0.01 kilogram meters squared. So now that we have all of this information, we are ready to start solving for all of the unknowns and most importantly the height in this situation. So let's write out conservation of energy and then let's slot in everything that we know. In conservation of energy, we are saying that KE1 plus PE in photo 1 plus the work in from any forces minus the work out from any forces, like friction, is equal to KE2 plus PE2. Now, initially the bucket isn't moving, the wheel isn't moving, there's no KE1. But the bucket is elevated and we don't know at what height. So what PE1 is, we don't know. Or maybe a better way to think of it is actually PE1 is going to be 0. And the reason why I say that is that this bucket is very close to the x-axis. It's going to descend from there, so it's going to get further away. It's going to go in the negative direction below the original level of the x-axis. So that being the case, I'm going to set my PE1 to be 0, and I'm going to treat PE2 as being negative because the bucket has descended beneath the x-axis. Again, that's totally legal to do. Potential energy due to gravity is allowed to be negative. Work in. There's no jetpack anywhere in this question, so there's no work in. Work out. There's no friction in this question. There's no work out. Is equal to KE2 plus PE2. So that gives us that 0 is equal to the kinetic energy in photo 2 plus the potential energy in photo 2, remembering of course that PE2 is going to be negative because this bucket is under the x-axis. But here is where we have to realize something very important. The kinetic energy in photo 2 is coming from two different places. One is the linear kinetic energy of the bucket, and the second is the rotational kinetic energy of the wheel. And we have to account for both of these inside kinetic energy. So what we have is, we could say something like this. It's equal to the kinetic energy in photo 2 due to the bucket plus the kinetic energy in photo 2 due to the wheel plus potential energy in photo 2. Now let's start expanding all this. 0 is equal to, the bucket is moving in linear motion, so linear kinetic energy is 1/2 mass times velocity squared plus KE2, the wheel, or I suppose I've been using the letter P to stand here. The kinetic energy of the pulley is the kinetic energy due to rotation, so that's going to be 1/2 times I times omega squared plus PE2, that's mgh, where m is the mass of the bucket. So the kinetic energy of the bucket, 1/2 mb v2 squared, plus 1/2 the moment of inertia of the wheel times angular velocity squared, plus mass of the bucket times g times the height, the negative height that it has here, will all sum up to 0. All right, let's keep going. Let's substitute in everything that we know. 0 is equal to 1/2. Mass of the bucket, 5. Velocity of the bucket as it strikes the surface of the water. We were actually told this. I should have written this down. The velocity of the bucket as it strikes the surface of the water is 8 meters per second. Plus 1/2 I, we already calculated that as being 0.01, times omega. Oh, now we have a bit of a problem, don't we? We never calculated omega. Fortunately, we were given one piece of information. That is that this wheel is rotating and the rope is not slipping on it. That means that the distance that the bucket fell is equal to the distance the rope traveled. The distance the rope traveled is equal to the distance that the rim traveled through. The velocity of the rope equals the velocity of the rim. And if that's the case, then we can say that the velocity of the rim, the linear velocity, is equal to the angular velocity multiplied by the radius. So the linear velocity of the rim is going to be the same 8 meters per second because the rim is moving along with the rope, which is in turn moving along with the bucket, is equal to angular velocity, not yet known, multiplied by the radius, and we were told that the radius was 0.1. So 8 divided by 0.1 gives us the angular velocity of the wheel, of the pulley, and that's going to be 80 radians per second. This is the number that then gets plugged in to the calculation for the kinetic energy. This is the angular momentum, and it gets squared. Plus, now we can turn to the potential energy. The mass of the bucket, again, 5, g, 9.81, times the unknown height. Okay. Now, let's start simplifying all of this. All right, 5 times 8 squared. 8 squared is 64. 5 times 64 gives us 320. Times 1/2 is going to give us 160. Plus, 80 squared is 6400. Multiplied by 0.01, that gives us 64. Half of that is 32. Plus, 5 times 9.81 times h, that's going to be 49.05 h. And now it's very simple to solve for what h is. So I'm going to continue this calculation on this side of the page. I'm going to subtract 160 plus 32 from both sides. 160 plus 32 gives us 192. So that's going to give me negative 192 is equal to 49.05 times the height, negative because I subtracted these from both sides. And so the last step is just dividing by 49.05. So negative 192 divided by 49.05 gives us negative 3.91. So the height that this bucket had to fall to, its height in the final picture is negative 3.91 meters. So that is its position relative to its original starting point. That is how far it has fallen. So to summarize the way that we solved this question, we first solved for the moment of inertia, we wrote out conservation of energy, and then we started expanding the terms out. Now, there were two things that we said here. First of all, because the bucket is originally very close to the x-axis, I said there was no potential energy due to gravity, on the understanding that there would be potential energy at the or a negative potential energy at the surface because it's below the x-axis. The other thing that was important is in photo 2, there are two different types of kinetic energy. One kinetic energy coming from the linear motion of the bucket, and a second kinetic energy coming from the rotational motion of the wheel. When we expand everything out, we were given the linear velocity of the bucket as 8 meters, but we had to solve for the rotational velocity, which was easy to do because as long as things are not slipping, the rotational velocity times the radius will just give you the linear velocity. So that's the value that we had to plug in to conservation of energy. The only thing that was unknown here was the height. And from this point onwards, it becomes a straightforward algebra question, and we can easily find that the height was negative 3.91 meters.
When an object rolls without slipping, it moves linearly and rotates at the same time. We have to account for both forms of kinetic energy, linear and rotational, in the same object. Consider this puzzle. A 10 kilogram ball with a radius of 0.1 meters is at the top of a ramp. It is at rest at a height of 3 meters. It rolls down the ramp. What is its linear velocity at the end of the ramp?
In this question, we have a ramp, and we have a ball that is rolling down that ramp. The ball starts at the top. Let's call that photo 1. And it winds up at the bottom. Let's call that photo 2. I'm going to set my x-axis, my level that I'm starting all of these calculations at, to be on the surface of the ground. I'm going to set positive y to be in this direction. And the original height of the ball, on the basis of its center of mass, is 3 meters. Now, let's write down all of the information that we know about this ball. Its mass is 10 kilograms. Its radius is 0.1. And we need to know its moment of inertia because that's going to play a big role in this calculation. The moment of inertia for a solid sphere, you can find this in your textbook, by the way, it's given as 2/5 times mass times radius squared. So in this case, that would be 2/5 times mass 10 times radius 0.1 squared. So that's 2/5 times 10, that would be 4, times 0.1 squared. 0.1 squared would be 0.01. So when you multiply all of this together, you get 0.04 kilograms meters squared. Okay, so now we have the moment of inertia that's going to play a role here. Now, let's go ahead and let us start writing conservation of energy. Conservation of energy tells us that KE1 plus PE1 plus any work that comes in minus any work that goes out equals KE2 plus PE2. So, in photo 1, the ball is not moving. There's no KE1. But there is PE1 because it's starting from above my x-axis. So we need to keep this term. Work in, there's no work in, the ball is not wearing a jetpack. Work out, there's no friction in this question. So we don't need to worry about work out. More correctly, I should say that there's no energy lost to friction in this question. KE2, the ball is definitely moving when it reaches the bottom of the ramp. And more importantly, it's rolling. Rolling means it is both moving linearly and rotationally. So we're going to need both of those terms when we expand this out. But the potential energy, there is no potential energy. So we can eliminate that term. So if we were to simplify what we have here, we can say that the potential energy due to gravity in photo 1 is equal to the KE due to translation in photo 2 plus the KE due to rotation in photo 2. Because this ball is both, like I said, moving horizontally but also spinning at the same time, we have to account for both. Now, let's expand this out further. mgh1 equals KE2, that's the translational kinetic energy, the linear kinetic energy, equals 1/2 mv2 squared plus KE rotation, that's going to be 1/2 I omega squared. So one thing that you've probably noticed is we have a v squared here and we have an omega here. Many of these other terms we've already worked out. Moment of inertia we've already worked out. Mass we know, stuff like that. The only thing that's left is the relationship between v and omega. So that's going to become important later on. But for now, let's substitute everything that we know. Mass, 10. G, 9.81 height 3 equals 1/2 mass 10 v2 squared plus 1/2 I 0.04 times omega 2 squared. Okay, so 9.81 times 3, that gives us 29.43 times 10 is going to give us 294.3 is equal to 5 times v2 squared plus half of 0.04 is going to be 0.02 omega 2 squared. So now it looks like we're stuck. We have one equation, but we have two unknowns. How do we proceed from this point? The answer is there's one other piece of information we were told, and that is this ball was rolling without slipping. So if it rolls without slipping, then this equation, velocity is equal to angular velocity multiplied by radius, applies. We are solving for the linear velocity, so this equation can now have the term omega r, or I can rewrite this equation so that we can write this in terms of omega. I could say that omega is going to be equal to v over r. And I can take this and I can plug this in for omega over here. So that's going to give us 294.3 is equal to 5 v2 squared plus 0.02 v over r whole squared. Okay, the radius we know. The radius is 0.1. So what does that give us? That gives us 294.3 equals 5 v2 squared plus 0.02 v squared we don't know yet, divided by r, but r was 0.1, and that gets squared too. So 0.02 divided by 0.1 squared. 0.1 squared is 0.01, and 0.02 divided by 0.01 is just going to be 2. So that's going to give us 294.3 is equal to 5 v2 squared plus 2 v2 squared. So 294.3 equals 5 plus 2 gives us 7 v2 squared. So if I divide both sides by 7, 294.3 divided by 7 gives us 42.04, and then take the square root because that was v squared. That's 6.48. So the linear velocity of this ball is 6.48 meters per second. And we have now solved this by using the linear kinetic energy of the ball in tandem with the rotational kinetic energy. We applied both of them at the same time, and then we solved for the linear velocity.
In this video, we explored work and energy in rotation. In the next video, we will explore the last and most important topic in rotation, angular momentum.